We now welcome Dr. Jean-Noël Houchat from National Autonomous University of Mexico, who is going to show that long-term aversive memory is promoted by the presence of uh, conspecifics in the lobster cockroach. The floor is yours, Jean.
Thank you very much. So my talk will be about a study we conducted in Mexico, as the speaker said, on the modulatory effects of the presence of conspecifics on associative learning and memory in a cockroach. So to begin, what do we refer to when we are talking about associative learning in insects? So we can imagine a context in which an insect perceives a chemical or visual stimulus in its environment. This stimulus can be, for instance, a scent, some food cue, a floral resource, as in the case of a pollinator, or a mate. At first sight, the stimulus would induce a basic positive or negative response, but we all know that is not so linear. Indeed, there is a broad literature showing that insects are able to associate a stimulus with either a reward or a punishment, then adapt their behavior to the situation with an enhanced positive response to the stimulus associated with a reward, or an enhanced avoidance behavior when the stimulus is associated with a punishment. This ability is known, according to the situation, as appetitive or aversive learning, but it does not stop here. Because the memory of the learned behavior can be stored over a more or less long time. In general, in insects, if a learned behavior persists for a few seconds to minutes, we can talk about short-term memory. If it's a question of few minutes to few hours, we can talk about medium-term memory. And if it's a question of few hours to at least 24 hours, we can talk about long-term memory. It is well known that in insects, mates are used as key stimulus, in particular because they produced pheromones and other chemical cues to ensure orientation behavior for mating or aggregation. But it has been shown that mate cues are modulators of associative learning as well. In the present example, male adult moths associate more easily the scent of geraniol to sucrose when they are pre-exposed to the female sexual pheromone. Although this is a short-term effect compared with naive individuals which have never been exposed to the pheromone. Such modulation takes all its importance in eusocial species, for instance, in the case of the bees' waggle dance, where individual learning performance influences the collective foraging behavior in the colony. But there is quite poor knowledge of the effects of mate cues on associative learning and memory in colony living insects displaying a lower level of sociality. To address this question, cockroaches are a good model because they are subsocial insects. That means that there is no reproductive division of labor or caste in the colony, but parental care can be provided to the offspring. Here, individuals gain some benefits from group living in terms of temperature, reduction of water loss, or collecting foraging, as here. If we take it into account, we can therefore expect positive effects of the presence of conspecifics on individual learning because it would be, in turn, an advantage for guiding collective behavior. To test it, we used adults of the lobster cockroach Nauphoeta cinerea, which is currently used as live food for some exotic pets, such as reptiles and amphibians, which is quite cheap, very easy to rear, and very prolific. And above all, whose sociality is limited to poor parental cares, consisting in brooding neonates for around 1 hour after hatching. To do this, we made a dual-choice device which consisted in a tunnel divided in 3 identical areas. In one of the lateral area, a box containing a bait was presented, whereas the opposite area was left empty. Then a cockroach, starved for 3 days before the experiment, was put in the liftall middle jag there. To punish insects entering the stimulus area, we made 2 combs with strips of aluminum foil laid on the tunnel floor and connected to an electric shock box. Here we named it ACE-B. So 3.5 volt shock was delivered to every insect touching both combs simultaneously there, as it closed the entire circuit. Each experiment was run for 10 minutes and 4 behavioral responses were possible. Insects were said unreactive if they remained all the time of experiment in the middle area. If they left the middle area but didn't stay more than 60 consecutive seconds in one of the lateral area, it was considered as undecided. And if it remains more than 1 minute, 60 consecutive seconds in the same area, it was considered as choosing for the stimulus or for the absence of stimulus. We used fresh apple pieces of identical dimensions as baits, which were replaced between each experiment. We performed 3 sets of experiments. In the first one, we assessed the directed responses induced by the bait. We pre-exposed a group of insects to the empty device, and we offered a bait to another group. Once they entered the stimulus area, we immediately put them back in the middle jail and tested their behavioral responses. We also tested if these responses were maintained 20 minutes and up to 24 hours after the pre-exposure session, which corresponds to middle and long terms. In the second set of experiments, we tested the learning performance of cockroaches. We applied there a unique shock to every cockroach entering the stimulus area. Then we tested them again for a short-term memory. For the last set of experiments, we did that in absence and in the presence of a conspecific in the stimulus box itself. For the last set of experiments, every punished insect choosing the bait there at a short term was discarded for testing medium and long-term memory. We first found that the presence of a bait did not induce significant changes in the proportion of cockroaches exploring the tunnel, nor in the proportion of undecided insects. But we observed a random choice for one or another lateral area in the empty device that became a significant choice for the stimulus when a bait was offered, which means that the bait itself induced a directed response, and this response was maintained up to 1 day. When we tested short-term aversive memory, we observed that most punished cockroaches did not display changes in their exploratory behavior nor in their undecision rate and kept choosing the bait. But individuals that formed aversion among these individuals were able to store aversive memory differently depending on the absence or the presence of a conspecific. In absence of conspecific, no significant differences were found between control insects at short term and punished insects there tested for medium and long-term memory. We just noted a slight decrease of exploration at 24 hours, but it was similar to that we observed in control conditions. And in the same way, punished insects displayed random choice for the bait at 20 minutes and 24 hours, but the proportions of cockroach were very similar to those observed in control condition. Now, in presence of conspecific, we observed a significant reduction of exploratory behavior at medium and long term. And we also noted a random choice for bait, but the decrease of proportion was stronger than in absence of conspecific at medium term. To resume this result, we found that aversive learning is modulated by the presence of conspecifics in the lobster cockroach. Few cockroaches were able to associate bait and punishment independently of the presence of a conspecific. So, we cannot discard that multiple trials would improve learning success. In the lobster cockroach, several training sessions are often necessary for association. But here, cockroach is able to form aversion after a unit trial, form long-term memory of this aversion if they are exposed to conspecifics, which is not the case of insects learning alone. This is traduced by a low motivational state of cockroaches, which stop searching for bait and remain immobile in the experimental device. Now, in a colony, we can expect this enhanced individual learning performance to optimize collective behaviors. For example, we can imagine a concrete situation where individuals that keep memory of some adverse conditions they have experienced influence naive members of the same colony, leading to a general avoidance behavior. What we don't know is how the modulation of learning performance occurs. For example, we don't know the chemical cues responsible for the modulation, nor the neurobiological pathway responsible for aversion and interacting with these cues. This is what we aim to do in future studies. First, we want to identify this cue or these cues, and the sexual pheromone appears to be a first good candidate, as it is already known and characterized in the lobster cockroach. But we cannot discard, for example, some cuticular substances. In parallel, we want to test the involvement of dopaminergic pathways. Because what? Because they are involved in the formation of aversive olfactory memory in a variety of insects, and changes in dopamine levels are known to regulate the motivational states of insects and the initiation of a lot of behaviors. So this is the end of my talk. I hope you liked it, and I will be pleased to answer, or at least to try to answer your question. Thank you for your attention.
Thank you, Noël, for the fascinating presentation. We have some questions from the audience. So the first one is from Buster. How do they learn from things that trick them, like plants that smell like female pheromones, but get them trapped inside and unable to climb out? Do you have that information?
Oh, sorry. I had a problem for my no. Hi, sorry. Do you hear me?
Yeah, I can hear you. Can you hear me? Okay.
Can you repeat the question, please?
Okay. Pastor asked, how do they learn from things that trick them, say like a plants that smell like female pheromones, but get them trapped inside and unable to climb out. Can they learn from that situation?
Sorry, I don't hear you. Maybe I will go to the YouTube. Say,
Can you hear me now?
yeah. Yeah, I went to the YouTube
Hmm.
streaming to read the question. How do they learn from things that trick them, like plants that smell like female pheromones, but get them trapped inside, unable to climb out? Oh, I don't know. I don't know. I just concentrate myself on the communication of two insects. I did not
Hmm.
study any third
Hmm.
protagonist of this kind of relation.
Hmm.
But what I understand from this question is that a plant that smell like female pheromones.
I think it seems like the question is about whether the insect can learn from the situation that is not the real. For example, you have the chemical or something that smell like the female pheromone, but when it go to that situation, it realize that it's not a female pheromone, it's not a
Mhm.
female cockroaches.
Yeah, and in
Whether
general, in
it,
insects,
mm,
I don't think that a plant can emit
mm,
a sense uh, which is similar
mm,
to a pheromone compound, because the
mm,
pheromone compound itself
mm,
is a blend of a lot of components.
mm,
And plants, I think, or maybe I think, will produce secondary metabolites
mm.
which are not necessary blends, but particular, so unique molecules.
Okay,
So I
right.
don't know
Mm,
really if a plant, I know a plant can attract an insect,
mm,
but I'm not sure.
mm,
I'm not sure it can emit
mm,
the effect of
mm,
it can emit the effect of pheromone by attraction, but it will not produce something chemically
mm.
similar to a pheromone, which is a blend.
Okay.
I
Maybe
don't know if
I have another question.
I don't know
Mm.
if it was a exact purpose of the question.
Okay. Maybe I have the last question. How do the cockroach respond to the electrical stimulation in your experiment? Whether they just run away or they respond differently?
And we observed, because I didn't do this series of experiments alone.
Mm,
In the lab I worked in Mexico, I was working with an internship student who did an excellent work.
mm,
And cockroaches could adopt a lot, well, various reactions when they receive the punishment. Most of them didn't react directly.
mm,
They presented some latency in their reaction. I mean, they received the electric shock, and they run back, of course, to where they were released. That means in the center of the olfactometer. Uh, and there was when they run back to the center of the olfactometer, we enclosed them already in the middle J.
mm,
Uh, at short term, that means immediately after the punishment, there was two very recurrent responses. Half populations of cockroach did not move yet. did not move anymore. They remain immobile in the center of the olfactometer. That was the main response we observed. But there was another response when they remained immobile and suddenly they ran away toward the stimulus. I don't know what happened there, toward the stimulus. And after, they run back to the opposite area that was left empty. Maybe there was a neurobiological responses with certain latency to explain this mechanism, but I don't know what is.
Okay, great. Thank you.